Hey everyone, today we're going to talk about different tools for measurement that we're going to use this year during physics. Most of these, I would think almost all of these, that we're going to go through, you have probably used before, with the exception of maybe one, which I will explain here in a moment. But to kind of review from what we did yesterday with our lesson on units, we have here the prefix table for powers of 10. And I want to put two little notations on here that can just kind of be used as a reference for doing simple unit conversions in the metric system. And on either side here of this table, we have two different arrows, one pointing up, one pointing down. And these are kind of indicating, for example, this one on the right here, if we are moving from a prefix like tera, 10 to the 12, and moving to a smaller prefix such as hecto, we are going to want to move our decimal place to the right. So if we're going from a larger unit to a smaller unit, our number should be getting bigger since there are more of those smaller units inside of the larger unit. Which means if we're going from a smaller unit such as nano to a larger unit like kilo, we are going to move our decimal to the left. And these can be used just for simple conversions, comparing powers of 10, subtracting, and determining how many spaces we are going to be moving the decimal. We can also set that up with dimensional analysis, which I'll show you guys in a little bit of a later lesson. Different tools for measuring. As far as measuring length, everyone should pretty much know this object. We're going to use a metric ruler to measure the length of an object or the length that a object moves, the path that it takes. We could also use a meter stick like we did in our Barbie doll lab. Now to kind of give you a little shorthand notation here for some simple conversions, if we're converting a measurement that's in centimeters, 2 meters, and this would be times 10 to the minus 2, 2 times 10 to the 0, which if we go back up here, this would be from a centi to a base unit. And according to our little prefix here, we're going to move the decimal to the left. And this can also be accomplished by dividing by 100. If we're going the opposite way, we would then move our decimal place to the right, since we'd be going from a base unit to a centimeter. Or we can multiply by 100. Because that's a difference there of a factor of 2 powers of 10, from the 0 power to the minus 2 power. And that's how we get our 2 zeros on our conversion factor of 100. Measuring mass. We use this device a lot in chemistry. The amount of matter that's contained in an object is known as the mass. And we can measure that with either an electronic balance or the old school awesome triple beam balance. And this kind of follows the same procedure as far as converting with length. If we want to convert a measurement from grams to kilograms, or from times 10 to the 0 to times 10 to the positive 3, that's 3 spots, we can divide by 100, or excuse me, 1,000. So we have a factor here of 3 powers of 10, which means our conversion factor should get 3 zeros. When we convert the opposite way from a larger unit into a smaller unit, again, we can move that decimal place 3 spots to the right, or we can multiply by 100. Excuse me, again, 1,000. I'll get it. Measuring time. Pretty straightforward, pretty simple. We are going to use one or maybe two particular devices this year to do this. When you see elapsed time, what that means is time measured with a stopwatch or clock which we would, to the best of our ability with the precision that the device has, round it to the nearest hundredth. Now, a couple conversions that you kind of are just going to need to know, and I'll set this up with fractions, because we're ultimately going to use this with dimensional analysis. In one day, there are 24 hours. In 1 hour, there are 60 minutes. And in 1 minute, there are, you guessed it, 60 seconds. So we can use those simple time conversions. I don't think we would do much of anything beyond 1 day. But we're going to need these, and these are not given to you on your reference table. We're going to need these in order to convert time. For example, the display of a stopwatch is shown below. 4 minutes, 28 seconds, and 17 hundredths of a second. Convert, that should say convert the elapsed time shown on the stopwatch to seconds. Well, we know by looking at this that we have 28.17 seconds. But we also have this other part, which is in minutes. Having different units here, seconds, minutes, we can't just add these together. We have to make sure that they're in the same unit in order to combine them. So what we'll do, we know we have 4 minutes, and we know from our conversion here that for every minute we have 60 seconds. Now we're going to rearrange this a little bit in order to cancel out our units. And we're going to say that there are 60 seconds for every 1 minute. What this does, when we multiply this through, it's going to allow our minutes to cancel. 4 times 60 will give us 240 seconds. We're left with seconds. We can now add that to the 28.17 seconds. These are not completely aligned. Apologize. We add these together and we end up with 268.17 seconds. And we have satisfied what the question had asked. Measuring force. Most of you have probably used this device before. I'll have some in class for you to kind of play around with and just see exactly how they work. These devices do require gravity. And that's really what's going to be the force that we are essentially measuring, which we otherwise known as weight. So a push or pull on a mass, which is essentially any object, is what we call a force. Pushes or pulls. And we measure these with a spring scale, which we can see this hand over here holding a spring scale. We got a weight at the end here. Maybe this is a 5 kilogram weight. As gravity pulls this weight down, we see a force being or pulling the scale and the spring scale downwards, and we can then measure the number or the reading that we get on the spring scale to determine the force, which we would measure in newtons, represented by a capital N. Or, to kind of review with what we did today, a kilogram times a meter per second squared, which is equal to a newton. The third page of these notes was not included in your packet, and I did not get these out to you today before you left. So this last part here, I'm going to put on a video, and you guys might have to, you can either write this down on a piece of paper and transfer it, you can look at it later, and complete the notes. I'll leave that up to you. So measuring angles. The common unit for measuring angles, hopefully everybody knows this, is the degree, measured with that small little circle on top. And a degree is actually 1/90th of a right angle. And we're going to use these devices. I'll try and draw one here. I'd say that that's fairly decent. I might get too far here. This is a protractor. These are used to measure angles. We'll review in class exactly how to use this to measure angles, because you will be sketching and drawing scale diagrams, and we'll be actually using a protractor to not only measure but to draw in angles as well. So this leads us into a little bit of a review of trigonometry. Now if we consider a right triangle, we'll look at the relationships between the sides and the angles. If we consider the triangle with sides A, B, and C, we know that this is a right angle, and this is some unknown angle, we'll call it theta. Now, the rule that relates sides A, B, and C together is Pythagorean theorem, which says the square of side A plus the square of side B is equal to the square of side C. So if we know two sides, we can find the third by using that theorem. We can also relate the sides of the triangle to an angle, the ratio of the sides to the angle in the triangle. For example, if we consider our angle theta there, sine theta is the ratio between side A and side C. Cosine of theta is equal to the ratio of side B to side C. And the tangent of theta is equal to the ratio of side A to the ratio of side B. Let's do some examples here. A block is displaced a vertical distance of 0.75 meters as it slides down a 1.25 meter long plane inclined to the horizontal. Now I like to sketch this out and draw in my objects here. This is a little box, crate you might want to call it. We know that this block has a vertical displacement of 0.75 meters, which means off of the ground, this is about exactly 0.75 meters. And it is sliding down a 1.25 meter long plane. So the ramp that it's on is actually 1.25 meters long. We can complete this triangle. We know that this is a right angle. We now have a sketch of what is happening in the question. How far is the block displaced horizontally? So what we're looking for, from where it starts at the top of the ramp here, we're looking for how its position on the x-axis changes from the top of the ramp to the bottom of the ramp. And this distance is also known as b. So we can use, since we know 2 out of the 3 sides, we can use Pythagorean's theorem, a squared plus b squared equals c squared. We know that a is equal to 0.75 meters squared plus b squared equal to 1.25 meters squared. This comes out to 0.5625 meters squared plus b squared equal to 1.5625 meters squared. Simplifying, we get b squared is equal to 1. We take the square root of b squared and the square root of 1. B is equal to 1 meter. This would actually be 1 meter squared. We'll keep our units consistent here. What is the measure of the angle of inclination on the plane to the horizontal? So we're going to look at the angle of the ramp here compared to the horizontal. So there's our theta. We can use several different relationships here to compare the ratio of sides to the angle. I'm going to use sine theta, which is equal to the ratio of side A over side C. We can plug in our information. I'm just using those because those came directly from the problem. It's not a number that I calculated. It's trying to avoid some error here. So sine theta is equal to 0.75 meters over 1.25 meters. Now, if we punch this in, we get a ratio of 0.6. Our meters here are going to cancel. We punch this in. We want to make sure our calculator is in degrees. And we would get 30 degrees. This should be just sine. I know I'm going to get lambasted for this tomorrow, but live and learn. We're right at the end here. Theta equals 30 degrees. Bring your questions in tomorrow. That's all I have for you today. And enjoy the rest of your day.